Well, I'm Steve Croft, and here with Don Cleveland, winner of the 2018 Breakthrough Prize in Life Sciences. Congratulations.
Well, thank you very much.
Your father was a physicist. Can you tell us something about his work?
So he was a physicist, and he developed something that in the end of World War II that's not still on every aircraft in the world. It's called a static discharge Er, and if you have the chance to sit behind the wing in one of those cheap seats behind the wing, and you'll see that there are 3 or 4 or 5 of these things, about a foot long, on the trailing edge of the wing, and they were placed on aircraft in 1944, and now they're on every airplane in the world.
Did he take an interest in his work as a boy?
He grew up on a farm. He was the first educated person in his, or college educated person in his family, and actually I never asked him when did he really begin an interest in physics.
But how about you when you were a boy? Were you following closely what he was doing?
I did, and I was always going to be a physicist. People have asked me, so when did you make that decision? And I just never made it. It was always made. And it wasn't made by my parents for me. They didn't push me. It was just I was just always going to do that. And then I went to graduate school, and I got a degree in physics, an undergraduate degree in physics at New Mexico State. And then I went to Princeton, and I realized that they're really smart. And I switched from fluid dynamics to biochemistry, having never taken a biology course. After making that decision, I never looked back. It was a great time for biochemists. 1 or 2 or 3 people, a team of 3 could do anything. And it was just very, very rewarding. And I thought I was always going to be in science, and now I'm really pleased that I chose to be in biology and medicine.
I believe later in life your father unfortunately suffered from Parkinson's disease. Did that influence the course of your research at all? He
did develop Parkinson's, and it very much changed my childhood. So it wasn't even so late. It was in he developed the disease over a 10-year course. It's a fatal disease, and it made me. I realized the trauma that families go through. And actually, it's greatly rewarding now that nearing the mature phase of my career, we've developed a strategy that actually might be effective in Parkinson's disease. Yeah, so that's very, very rewarding. We haven't proven that it will really work yet, but it has a real chance.
Do the major neurodegenerative diseases have anything in common aside from affecting the brain?
The major neurodegenerative diseases do have things in common, one of which is that where we know that there are genes who contribute to the disease, we know that the genes in all of the major diseases are expressed in many cells of the nervous system, very broadly, not just in one kind of neuron whose degeneration causes the disease. And so we demonstrated that in a form of inherited ALS, the disease is really a disease of the system. The primary neuron whose dysfunction causes paralysis, but it's driven by damage in the surrounding cells. So the message was really that it's a disease of the neighborhood. And it's sort of obvious now, and it's obvious as a real-world example. The quality of most of our lives is really determined in part by our neighbors. And we demonstrated that in ALS. It's now recognized to be true in Huntington's, and most recently, it's absolutely true in Alzheimer's disease. So yeah, there are some general lessons.
What is it that makes these diseases so hard to treat?
So why are they so hard to treat? Well, until very recently, with the lamppost of genetics, we really didn't know where to start. So the genetics has given a real entry point of where you know what goes wrong. And in the cases in almost all the cases where we know the genetics, we know that the individual inherits a gene that encodes a product that's bad. We don't always agree on what the bad thing is, but if you could just turn off the bad gene, you would be directly targeting the disease mechanism. And that's what we've done. The team, that's what we've done, is to develop a strategy to use designer DNA drugs. put into the nervous system, they get taken up by cells all over the nervous system, and you can silence specific genes. That's why we call them designer, because you design it little snippets of DNA. Of course, you may remember that DNA is the substance of the genome, and you have a bunch of genes, and they're made up of DNA, and little snippets of DNA are able to silence the expression of individual genes.
And is there a danger that there are unintended consequences as you tweak one thing, you cause something else?
Of course, there's a danger that for example, if you turn off a gene completely, the gene probably did something good as well as when mutated, doing something bad. So the strategy that we've used, we get to dial it up and down by changing the dose. So of course there's a risk, but if you have a fatal degenerative disease, it's probably worth the risk.
Right. Do you think we'll ever fully understand the brain?
Oh, fully understand the brain, of course. No. But will we understand much more about the brain? Yes. Are we near the end of that understanding? No. We are at the very beginning of that. And that's actually part of the excitement. So even beyond the medical arena, just how does it work? And to the young folks out there who think, well, everything's known. No. Almost nothing is known. And so it's a truly exciting time for discovery, especially in the nervous system.
Great. Well, thank you very much.
My pleasure.
Thanks.